For anyone who noticed, that was a D3 graph, actually, in the back there. I'm Alice, and this is Grant, and we're software engineers at Ravelin, where we fight cybercrime.
Real heroes don't wear capes.
It's great to be here at LondonGophers and Deliveroo. However, we've got a confession to make. In order to convince the organisers to give us a speaking slot, we tried to squeeze as many technical buzzwords into our submission as truthfully possible. And it worked. Now, this wasn't our actual submission, but more of a spiritual representation. But joking aside, at Ravelin, we are super excited about the current performance and future potential of machine learning with our vast stores of data. A few of us here in this room might even be training a model in a little black box as we speak. But then, what do you do with it? In a production environment at a commercial level, we are going to be wanting to hit it at speed and scale. So we want to ask it a lot of questions very quickly and probably from a lot of different locations. At this point, it's not just about how good the model is, it's about how easy we can talk to it. So, in the next 25 minutes or so, we're going to be looking at two ways of doing this. So first, it's an out-of-the-box solution called Tensorflow Serving. And the second is using a language of choice method, which for us is Golang. And if that's not exciting enough, we have a t-shirt giveaway. For anyone who spots the code error, and that's code error in the slides, not in the live coding, because live coding. Right, now before we dive straight in, what does Ravelin do and how does it fit into all of this? So, at LondonGophers, with all of these amazing talks, you might be having a beer or 5, and the morning after, the night before, we're going to be craving something nutritious and delicious. At this point, of course, we will take out our favourite food delivery app, Deliveroo, and we'll select our menu, our choice, and it's at the point of checkout that Ravelin comes in. Via an API, we'll serve up one of 3 recommendations. We'll either say, yes, let this happy meal go through. 2, we should probably refuse this order. Or 3, block it because, frankly, they look fraudy. Now, if you're Deliveroo or Honest Burger, why should you care if someone's buying food from you using a stolen credit card? Well, you've given the food away. However, you don't get to keep the money. If the customer calls up the bank and says, this is a fraudy transaction, it's not the bank that pays them back out of the goodness of their hearts. It's the transaction's reversed out of your pocket as the merchant in what's called a chargeback. And then the bank then charge you a fee for the pleasure of that transaction. And here we're all thinking back to really nice people. And then, if this happens too often, the card scheme you're working with to take online payments, such as Visa or MasterCard, will start putting up the cost per transaction. And if it carries on for too long, they might not work with you at all, which is a bit of a kicker if you're an online e-commerce merchant. And then, of course, we've got angry customers who, rightly or wrongly, now associate you with fraud. I know I'm guilty of that. So these are all bad things. How do we stop these bad things from happening?
Yeah, so if we were to look at what a request might look like that comes from Deliveroo in a quick, simplified API sort of flow, we would get a request from API call from Deliveroo that says, this order's come in, it's for 12 beers, the customer's name is Grant, the payment is a company card, and the address is this place called Hotel Hangover. We then run a thing called feature extraction on it, and we convert 12 beers, and we say, well, we're pretty sure that's alcohol. This customer is a new person. We've never seen them before. No idea who they are. They could have just been invented. The payment, however, is a trusted card. We've seen these company cards before. They generally don't have chargebacks on them, and they generally don't run out of money either. And the address is in this dodgy postcode where, scooters don't come back from. So you probably want to watch that. And then we pass this in to our machine learning model, and it'll come back and say, we should deny this order. Now, this is all very well, and we spoke through that in, 30 seconds or so. Except when you click place order, we don't want to be sitting there watching the spinny thing for like 30 seconds. So we need this to happen within a second, or even faster, depending on who you're working with. So, what are the ways of doing this and serving this model? So, an out-of-the-box solution is a thing from TensorFlow called TensorFlow Serving. You can get it from your local cloud provider, and essentially you upload a model, and they give you an HTTP endpoint to hit, and it scales, and it works, and you generally forget about it, except when it doesn't work. So, let's quickly have a look at what happens when it doesn't work, and also just how simple this really is to run. So if we look at the Docker file, so instead of running this on a cloud provider, to test this, we're just going to run it locally, because then we're not dealing with all the overhead of going to the cloud provider to serve out predictions and all that. We can just test it locally and forget about network traffic for now. So we just say from TensorFlow Serving, specify version. We give the model the name because it needs to know the model so that it gives you a special endpoint with the model name in it, and we copy the model from the folder into the models directory. And in 5 lines, which is actually 3 lines of Docker, we have a TensorFlow serving thing that is going to serve your model using HTTP. So, if we get to the right folder here, and we can build this with a simple Docker build. There we go, Docker build, and we just need to build the right version. TensorFlow serving, and we're just going to tag it as testing for now. We can see that this is going to not work at all because you need a dot. And we should have an image. We can also have a look at that, and that image size, while we at it, images, how many images do you have, Alice?
5.
We can see there that it is about 223 megs. So the model in this case is actually about 200 megs on its own. So the overhead from TensorFlow Serving is about 20 megs. So that's not too bad. Let's actually run this, Docker run, and it is running. Cool. So we also have a little Go script that is going to test this, example 1. And we'll get into the testing script a bit later, but we can just go run, test. Sorry, can everybody see this? Yeah, cool. Okay, and we're going to just make this because we don't, you'll see here that there's TensorFlow is quite verbose with this logging, and it doesn't actually log when you start predicting, so we can just make that a bit smaller and not care about it for now. Test.go. So what this is going to do is it generates requests all the time, and it basically hits the model with different requests, because if you keep on hitting it with the same one, then it kind of caches it and you're not actually testing how fast the whole thing is. So it generates new requests every time, and we're measuring the response time and how many of those responses were successful. So if we start running this, we get a nice output. This is tested using a library called Vegeta, so Golang, very cool. And we can see there that we get some nice metrics out of this. And we'll stop before Alyssa's laptop crashes, because we don't want that to happen right now. So this is all very well and good. We can see we get a mean, a 99th. They're all successful, and we get a more or less successful rate. In the meantime, because this takes a while sometimes, I'm going to try and shut down this Docker image. Okay, and you'll see that I'm going to Control-C it, and it just hangs. And we'll leave that for a while.
Here's one we made earlier. This is what happens when we ran the images. So on the x-axis, we've got the requests per second, and on the y, we've got a response time in milliseconds. And we can see that it all goes swimmingly until we hit 10 requests per second, at which point it shoots up and CPU load builds up. This is awkward because It didn't actually tell us that it had broken. It didn't tell us, let alone tell us why it crashed. And right now, our customers are staring at this spinny thing.
Not ideal. Cool. So, at Ravlin, we use Go nearly exclusively. We can't quite convince the front end to switch. However, TensorFlow is written in C++. Go, for those of you that know, is not written in C++. So, luckily, TensorFlow provides some bindings. So we have a simple one-line import, and we can go import from GitHub, and we can now run TensorFlow code in Go, sort of, through the C bindings. So, if we would actually look at this. So what I'm going to show you now is 70 lines is all you need of Go code to run a TensorFlow model using Go. Okay, so let's go. The first,
Before we start taking photos of the code,
oh yeah.
it is available on GitHub, which we'll share in the link afterwards.
Yes, and the presentation's also available. Basically, it's all available. Relax. Okay, so we start off with package main, simple, some imports for logging in JSON and HTTP, then the all-important line, importing TensorFlow. Cool. Then we go into our main function. First thing first, we need to load the model. So we have this TensorFlow model, and we go tf.load saved model. You tell it what directory your model lives in, because the model consists of a couple of files. It's not just a single file. And there's this serving tag string thing. So you'll have to talk to your data scientist, because they like to set that to all types of strange things. But generally, just ask them, and they'll tell you what that is. You can also inspect the model to see what it is, but we won't get into that. We're even going to do error handling in 70 lines. So there we go. Panic if something goes wrong. And then we're also going to be good citizens and defer the close of this TensorFlow model. Then we're going to actually add an endpoint. Now, some of you might be asking, why do you have such a long, strange endpoint there? And this is just to make testing easier, because that's the endpoint that TensorFlow Serving serves models on. So to use the same testing library and not to muck about with changing endpoints and stuff, we just serve it on the exact same endpoint, and then we don't have to change anything in our testing suite, because we're kind of lazy. Then what this handle function actually ends up doing is calling predict. And then last little bit of main, we listen and serve on port 8080. So if we look at predict takes the response writer, the request, and the TensorFlow model as inputs. And we have this prediction data structure that we need to get from somewhere. Obviously, that's going to come from the request. We decode the body. Also, this is going to depend on what model it is. In this case, we're using the ResNet model, so it's a 2D map of your image, what's it called, color values. We decode that, and again, write out a 400. Maybe it should have been a 500 if we can't decode it. Then, another bit of TensorFlow stuff. Tensor is equal to a new tensor. So the TensorFlow representation of the data is slightly different to the Go representation. So luckily, TensorFlow provides us with a nice wrapper function that does this conversion for you. Unfortunately, at the moment, it's kind of doing a lot of allocations, but there's a pull request that's about to fix that from a colleague of mine. Because when models suddenly start using a lot of memory, it's problematic. Anyway. So we create the new tensor, again, write out a 400. If we can't do that, maybe that should have also been a 500. And finally, we're going to call calculate using the TensorFlow model and the tensor that we have just made. Okay. Right, we'll get to calculate shortly, but basically, from calculate, you get this S value, and we marshal that into your prediction, and then you're going to write out your prediction. Also with all your error handling. That's not the very important or very interesting stuff. So, question? No. Okay, calculate. Again, you're taking the model as input and the input tensor, and you're going to return your list of float32s, which is the model output, and you're going to say here, run is equal to TensorFlow session.run. Luckily, we don't have to keep like one session open. Once you've loaded the model, it keeps the session in memory, and you don't have to worry about all of that. You give this part is the input, and there's two important things here. The one is the input node name, which again, you're going to have to talk to the data scientists about, and they'll tell you that is the input node name. which also goes through some strange string transformations between Python and C, but anyway. And then you also have an input here, which you have just decoded from your incoming JSON. And you have an output. Again, you're going to need to know the node name that the output comes from. In this case, wide NN probability and the sigmoid function of that. And as simple as that. You return any errors, and then you have to cast this output value into the value that you expect to get, which is, again, the TensorFlow representation and the Go representation are slightly different, so we have to put it back into a Go-friendly representation. And that is it in 73 lines. So, now what? Let us quickly look at what this then looks like in the Docker image that's actually going to build this. So, we start off relatively normal, and we say we have Ubuntu as builder. You need to install all types of things to get TensorFlow installed, and Go installed, and all of that. Install Go, unzip it, the whole lot. Pretty normal stuff. Set up a few environment variables. Then there's this part here. So there's a lib TensorFlow that you need to copy in. And this actually contains the C bindings that are also going to have to be in your Docker image to be able to run this. And you unzip those, and you configure the path for all of those. And you're also then finally going to do the build. And you're going to build this binary called, in this case, GOTF. So then we have also provided you with a nice script. And basically what you have to do is copy the C libraries that you need into a folder, because you're going to need those if you run this in a Scratch image. So we'll talk about Scratch just now, but essentially we then start from scratch and only copy in the libraries and the binary and the model, and we can run the model. So if we actually go and do this, coming back to our hanging Docker friend over here, it still hasn't exited. So this is another one of those things where you're running somebody else's Docker image and you don't actually know what's going on there. You pulled it from Docker Hub and now it just hangs around. So unfortunately what we have to do here is actually Docker, yes, and kill it, because that's the only way that we found to reliably get rid of it. Luckily it dies quite easily then. Okay. Let's go to example 2, and we're going to example 2. We're going to build that long Docker file that I just showed you. Build, I think I've got this in history.
In case you were wondering, this is my laptop.
And we're going to call it test go in this case, just to show that it builds relatively quickly, but it's all been cached, so it's going to in this case. And we have a test go. That all works. Now, I want to run 2 of these together. So what we're going to do is run a TensorFlow Serving version and the Go version next to each other, and then we can run the testing script and actually hit both of them to see the responses between both of them. So I've got a Docker compose file that just ups both of those 2 images that we've built, and this will also spit out a whole lot of output. But the important part now is that if we go to okay, and we go run testing test. We should once again, let's do that. Now we're going to have 2 sets of output. We're going to have one compiled version, which is the one we just built in Go, and we're going to have a serving version. And we can see that they're all kind of working. Okay, and because we are, again, testing the TensorFlow Serving version, we don't want to crash Alice's laptop that's running the presentation. So, we can talk about the results.
Okay, we're looking at a similar graph, this time using a model that's actually we use for our client. It's a lot smaller and a lot faster. So in the x-axis, we've got requests per second in the thousands, and in the y-axis, we've got response time, this time in microseconds. And the orange line is the TensorFlow Serving, and the blue line is where we use our own Golang Scratch Serving. You can see they've got a similar performance profile. So it takes a while to get started at the beginning. Goes fine, and then 3,000, 3,500. So CPU builds up, and we all know how that story ends. You might be asking, why haven't we done it on the same model? And you're right, so we did. And actually, they're both similar performance at 10 requests per second. They both die.
So yeah, just to reiterate that, we've got a Go version and a TensorFlow Serving version that are basically giving the exact same results.
So, what did we learn, actually? Well, Go, as you saw, was fairly simple. We did it in just over 70 lines of code. No C++ was learnt in the making of this presentation. It's pretty flexible. We are able to query the inputs for the model, so we can dynamically switch it in and out. It's fairly performant, as you saw, and what we saw, if our model, which sometimes take large inputs or outputs, if we G-zipped it, we can squeeze a little bit of performance by reducing the network traffic. If we wanted to add instrumentation, we just add a Prometheus endpoint. It's fairly straightforward, and with security...
Yeah, so we touched on it briefly, but how many people are using Scratch images to run their Go in production? Not enough, I think, is the answer. So essentially, Scratch means that you're starting with a completely blank Docker image again. So all of those dependencies that we installed with starting with Ubuntu, we can actually, in theory, a lot of those are security vulnerabilities at some point, and you have to monitor all the channels to know if there have been any security things that have happened with those. Whereas if we start from scratch and the only thing we're copying in is the Go binary, then the only security vulnerabilities we have to worry about are those in Go itself. So please use Scratch if at all possible. So you're starting from scratch. What that also means is that your image is a lot smaller. So that Ubuntu image, the from builder part in the beginning, that will come in at about 1.2 gigs or so, whereas I can show you, maybe we should just do that. If we go Docker images again, we can see that the one that we just built, TestGo, is 223. So it is exactly the same size as the TensorFlow Serving version. Once again, we have about 200 megs of model files and 20 megs of actual code in there. So depending on your model size, your model size is the thing that determines the size of your image. But 200 megs is a whole lot smaller than 1.2 gigs. What this essentially means is that if you're running this in Kubernetes, your scaling is a whole lot easier because you're not having these huge images that are having to start up every time. You can also add health checks. So we can monitor queues on and GC and all types of things like that, and decide to make our health checks start failing for Kubernetes if there's a backup in the queue or something within the pod. We can also, in general, just have more control, decide when we want to scale this, decide when we want to start returning 500s, or when we want to return a 400, or when we want to, what metrics we want to give out. So, in conclusion, TensorFlow Serving is really simple. There's 3 lines of Docker file, and you'll have something up and running in serving your model using HTTP. And it's performant, it's quick, and yeah, if that's going to work for you, then great.
Whereas Go, if I remember what all the emojis mean, is simple, flexible, performance, just as, gives you more control, scales easily, can add instrumentation, add health checks, and is slightly more secure. So which is better? Grand old, classic,
it really depends. So basically, what it comes down to is what's going to work for you. If you're a scrappy one-person startup and you need to get your model running yesterday, you're probably going to use TensorFlow Serving, and you're probably going to put it on the cloud. And they'll do all the hard work for you. But at some point, you might find that the cloud is too slow, or you don't like the way they handle errors, or you want to do something special with your inputs, or your inputs are too large, and then your network overhead's too high. And so you need to do something yourself. And the point is there are options out there. You don't need to learn another language. You can do it all in Go. And it is just as fast. So, yeah. We are around. There's a link and QR code to presentation stuff and
As
so
promised, yep. We're around. Also, are we hiring?
Oh, that depends. Did anybody see the error?
No. Or questions. Questions.
Any questions? Yeah.
We've got about probably at least 5 minutes for questions, so if you have questions, wave and Antonio will run with the mic. Over there. I can also help if anyone else has a question.
So I might have missed this, but did you figure out how to get it to serve more than 10 requests per second?
It depends on the model, is essentially the answer. If your inputs are it builds up a bit of a network backlog, and basically the incoming traffic is just too much for like one network endpoint to handle kind of thing. So essentially it ends up being scaling it. Or if you're, like in this case with Go, you can maybe zip the inputs and then you're sending in zip JSON instead of just JSON, and then you can reduce the network sort of load and you'll be able to serve more models, serve more predictions.
So no. Not with that model and not with the way we were doing it.
Yeah.
Cool, thanks.
Aren't there any serverless auto-scaling machine learning solutions? So you don't need to manage any infrastructure.
Yeah, so as I say, all the major cloud providers provide you with basically TensorFlow Serving as a service. So you can upload your model and they take care of all of it. But
Yes, but you pay for the number of containers, and by serverless I mean...
No, so they charge you per prediction generally. Yeah, so you pay per prediction, but you don't have any sort of guarantee of how long that prediction is going to take or where it's run or things like that.
So, okay, but the response time is going up to over 10 seconds.
Yeah.
So it doesn't auto-scale.
Sorry, so that's running locally. If you run it on their thing, results vary. Yeah.
Yes. Okay, thank you.
Cool.
We had a question over here as well, Antonio, if you can just one step along.
Thank you. It was still about pricing, so do you have like a good cut by running, let's say, Kubernetes GCP env yourself compared to TensorFlow Serving, for example?
We never actually ran it on the cloud because we found it was just too slow for us. So the stuff we're running in production at the moment, generally the prediction will take less than 3 milliseconds, whereas our average time for running it on any cloud provider was around 200 milliseconds. And like that's over our SLA. So we didn't we started running it there. We were running it in what we call dark mode, so sort of testing models and stuff. We saw the response times, and we had to make another plan.
Anybody else has any questions? I have a filler question. How the hell did you get this cool QR code?
Here's something cool.
Coolest
Like,
code I've ever seen.
QRmonkey.com. It's great.
That is awesome. All right, any serious questions, anyone?
Also, how do I get my name at the start of my show when I start it?
So, if you didn't hear, how do I get the name of my name at the start of the shell prompt?
Because that was sick.
That's the best part of the presentation.
Oh, there's a question over there. Just by the corner on your side.
Do you also write the models in Go, or do you write them in Python and then import them in Go to run them?
So we strongly encourage our data scientists to use as much Go as possible, but we haven't quite got them as far as doing the actually writing the models in Go. There's been a bit of work on that, and there's sort of more and more guides coming out on how to do it. But it depends a lot on the model type that you're doing, and you're going to end up defining a lot of these input nodes. And like one of our models, I think we saw the other day, had a couple of thousand different nodes, and you're going to have to sort of be essentially writing a lot of the stuff that's already written in Python again in Go. So your training might be slightly faster, but I don't think I see the point yet.
Anyone else? Any more questions?
We have a couple of t-shirts and socks and stuff if anybody wants to come and chat afterwards.
More swag. Oh, laptop went to sleep.
Great. Thank you, Alice.